All right. Good evening, everyone. So, I think students might join, but what we will do is we'll get started. So, today I have two problems, which is again related to your assignment. Um, so, today we will solve one of the problem in injector design and another problem in liquid rocket engines, in fact gas generator cycle. Okay, so I think in assignment there is this expander cycle, uh, but I'm not going to solve that. You If you have any questions in understanding that cycle, you can ask me, but we will solve gas generator cycle today. Okay. And if you have any questions while solving, you can stop me at any time. And if you have some doubts in the lectures or previous week's assignment, you can ask me once I complete these two questions. Okay. So that everyone will be in same page, and then uh, after I complete these two questions, after solving these two questions, you can ask me any doubts if you have. Okay. Um, Today we have, right now we have only two, Padmavati and Sri Lakshmi. Thank you for coming. Uh, so yeah, all right. Uh, will be we will start by uh, reading the question as usual. Okay. So consider a shower head injector. You all know what is shower head injector is, and determine the total number of orifices required for fuel and oxidizer, and also find the mixture ratio of the propellant. Okay. So there are three things you need to find out uh, from this question. So some of the parameters given. One is for oxidizer supply there are a few parameters, and for fuel supply there are a few parameters given. Um, Using these parameters, we need to find how much number of orifices we need for this fuel and oxidizer injector. Okay, so this is a kind of design problem, because usually we don't be usually the problem would be given and you will be asked to find out what is the mass flow rate or what is the volume flow rate things. But here the flow rate is given and you are asked to design the injector according to it. Okay, so um, there are few given data in the questions. Okay, uh, let me first explain you about the question so that you can tell me how to solve this problem. Okay, um, so the given problem is nothing but we have a fuel and oxidizer supply. Okay, and uh, so mass flow rate of fuel is given. This is the total mass flow rate, not through, I mean total mass flow rate through the injector, not through only one orifice. Okay, and then similarly we have, okay, let me write this as oxidizer 1.44 kg per second, and mass of the fuel or mass flow rate of the fuel is 0.48 kg per second. All right, and then we have CD of oxidizer, and then we have diameter of orifice. Okay, diameter of orifice in the oxidizer injector, which is 1 mm, and similarly diameter of orifice in the fuel injector, which is 0.85 mm. Okay, um, what else is given? The pressure drop is given through orifice. For oxidizer injector it's 0.25 megapascals, and for fuel supply it is going to be 0.15 megapascal, and density is also given. So how do we approach this problem? Does anyone have any idea how do we approach this problem? I hope the
Yeah,
problem statement is clear.
yeah. Hello, Mr. Ganesh. I have a question actually.
Yeah, sure, sure.
So, considering that this is a shower head injector, right? Like, so ideally the manifold would have the same pressure, right? So, why is it that the pressure drop across the oxidizer orifice is different from the fuel orifice?
So basically, it has. there are a lot of things that come into play. So the manifold is same, but the manifold for fuel injector and oxidizer injector is different, and that is the reason you have a pressure drop for oxidizer and fuel separately. Okay, so the manifold is not same for both fuel and oxidizer. Were you able to follow me?
Okay. So you mean there are
So there are two injectors. Okay, one is
oh,
oxidizer, another is fuel. This would
okay.
be oxidizer, and this would be fuel, and it will have uh, its own orifices.
Okay.
But it's possible to have a single injector with holes for both oxidizer and fuel, right?
So there are a lot of combinations of injectors available. There is also there is this doublet. You might you guys might have gone through it, right? So what happens? There will be this orifices. There will be this injector, and which has one for oxidizer and one for fuel. And what happens is, so let's say if you take a cut section, it is going to be something like this. So if you want to have it in an angle, it's going to be something like this, right? This is also a kind of injector where this here fuel comes and here oxidizer comes, okay? And then these both will merge here, and then it creates a fan, and then breakup will happen. All these things will happen. But the thing is, fuel goes through a separate orifice, and the oxidizer goes through a separate orifice, right? And the mixing happens outside the injector.
In this particular diagram that you have drawn, this is an impinging type, right? The two
Right,
things will impinge.
right.
Okay.
It is impinging, yeah. Two jets
Okay.
will impinge.
And there are some differences between the two, no? Like type of flame because of this. Is there something, some sort of difference, like impinging, non-impinging?
So the non-impinging is this shower head injector, where it will be the oxidizer will flow separately and the fuel will flow separately, but they will meet somewhere in the inside the combustion chamber and they will react. So that is going to happen. But in order to have a very well mixing, we have this inclined impinging injector.
Okay, okay. And what about hypergolics?
Hypergolics, that has I don't think so you need to um, confuse that with this. So hypergolics, what is hypergolics? It is when
Means,
when it can
it,
spontaneously
yeah.
react when it comes in contact with oxidizer, right? And the fuel,
Okay.
right? Isn't that
Yeah.
hypergolic? Right.
Means it doesn't need an ignition source.
Exactly. So here we might need a ignition source. Injector is just provides you fuel and oxidizer into your combustion chamber at some at a given uh, at a specified mass flow rate. Okay, so it
Okay.
just provides you the fuel and oxidizer into a combustion chamber. There, so this fuel and oxidizer could be hypergolic, and if it's hypergolic, when at the time of your impingement itself, it starts burning and then produces gases. So that has nothing to do with this injector.
Okay. I have one more question. Like this injector will mix the two things after atomizing the both fuel as well as the oxidizer.
Right.
So where will the igniter be located in this particular case? Like in solid propellant rockets, we know exactly the location.
Right. So let's say if this is your whole combustion chamber, and let's say these oxidizers are coming like this, and fuel is coming like this. Okay. It can be somewhere here. The igniter can be somewhere here, which ignites. Or so what is the major role of igniter. It has to raise the temperature of fuel and oxidizer to a certain temperature such that it reacts, right? So that is the main role of the igniter. So you can keep a igniter where this such that this fuel and oxidizer will reach at that point, and then you can give a spark or something. It starts burning. Usually,
Okay.
what happens if we um, so there is already, so initially you need ignition, right? At the start of the rocket motor you need ignition, and later that flame gets will when you supply fuel and oxidizer at a certain mass flow rate, that that flame gets sustained within the combustion chamber. You no need to ignite again and again or with a certain period of time. So it can
Okay.
be anywhere. It's up to the combustion chamber design.
Okay, like in case of big solid propellant rockets,
Mm-hmm.
sometimes we also use some small solid rockets for to act as an igniter, like the pyros and igniter and all.
Right, right.
Now, what about the liquid propellant rockets? Do we need a large igniter like that, or a small igniter can be more than sufficient?
So it you can think it like SI and CI engines. So what do you do in SI and CI engines? In CI engines, you no need a igniter because it is at high
Yeah,
pressure. It
yeah.
automatically reacts, right?
Compression engine. Yeah,
Ha ha. So in SI engines, you have a igniter and there is a spark coming in, and that spark is locally heating up the gases near to it, and then that heat gets propagated and temperature gets diffused, and suddenly a reaction happens, right? That is what
right,
happens again. So same
right.
thing you can apply here also. There can be spark ignition, even uh, pyrotechnic uh, i- igniters here also. So there should be some way that you are raising the temperature, or you maybe you can supply the fuel and oxidizer with a higher pressure so that it automatically gets ignited.
No, actually, what I was asking is compared to the solid propellant rockets, do we need more ignition energy in case of liquid or less? Like liquid should have less, I guess, but I'm not sure about that. That is what I'm asking. Like
Right,
in case of solid rockets, we do need sometimes a smaller igniter to ignite a larger igniter, and then the igniter ignites even larger, and finally the SRB catches fire.
right.
But what about liquids? Do we need something, some sort of cascade, or a small igniter is more than sufficient?
It depends on the fuel and oxidizer also. So if the it depends on how much energy you need in ignition, uh, and that varies based on the fuel and oxidizer. So you cannot generalize that solid. So this will require less energy than the solid propellant
Okay,
rockets.
okay.
Okay, so it
It's
depends
like
on
comparing apples and
various.
oranges. Okay,
Ah, yeah.
okay,
So it depends on fuels and various aspects, the pressure, all these things comes into picture. In solid, we can't do anything because we casted it before, and uh, we are casting the whole rocket motor before, and we are putting it inside the chamber. And we wanted that to be in not in a. We wanted that to be like not an hypergolic, right? Then we wanted to ignite it, so that is the safest way of operating that motor. Here it can be anyway. So ignition is something I think sir will uh, teach you in upcoming lectures, maybe. I'm not sure, but you can search for it in online. Basically,
okay,
yeah, basically the underlying concepts remain same. That is what you should know. You cannot generalize it. That's what I'm saying. Okay.
okay.
Coming back to Sri Lakshmi's question, is that clear, Sri Lakshmi? We have a two
Yes,
separate
yes, yeah,
injectors.
yeah. I
Okay.
didn't realize it was two separate manifolds. Yeah,
Okay.
this is clear now.
Okay.
Yeah.
Okay. All right. So let me remove this. So yeah, the question remains same. How do we approach this problem? So there's going to be pressure drop along the orifice, and there is a different pressure drops in oxidizer and fuel. Uh, Flow rate is given. We need to find what is the number of orifices required. Yes.
So we'll calculate the flow rate through each individual orifice
Okay.
and then divide the total flow rate by that one to get the number.
Yeah. So that is the concept. So there is going to be number of orifices, and each orifices is going to deliver the same mass flow rate, because the pressure drop along each orifices is going to be same in case of fuel. And in case of oxidizer separately, similar thing is going to happen. So each orifices is going to have some mass flow rate, and when you sum up all those mass flow rate, you will be reaching the total mass flow rate. Okay. So uh, we can even write mass flow rate of oxidizer to be the number of oxidizer orifices, and then mass flow rate through each orifices, mi. Okay. Or any I. So in each orifices, what is the mass flow rate? So now the challenge is we need to find what is the mass flow rate in each orifices based on the given data. Do you know any formula to do that?
We have to use the pressure gradient, sorry, pressure change to get the volume flow rate and then multiply it with the
Okay.
density.
Okay. So um, we need to guess. So what we know is mass flow rate is nothing but rho times volume flow rate, right? Isn't it? So rho of oxidizer times volume
Yeah,
flow rate,
right.
and then what we know about volume flow rate
Area into velocity, maybe?
of orifice into velocity of the orifice. Then how do we find velocity of in each and every orifice? So basically, there is already a formula given, but let's try to derive it if you want. There is this orifice, right? This is how orifice looks. If you have a closed loop, you want to find what is the velocity here. This is V oxidizer, right? And here the velocity is almost zero. Okay, it's not exactly zero, but it's almost zero because it's a big chamber, right? And the velocity is almost zero, and we are telling along this orifice is some pressure drop, right? So what you can do is you could do a apply a Bernoulli equation here. And what does Bernoulli say? So here, let's say this is 1 and this is 2. So what we know about Bernoulli? Bernoulli is P1 by rho 1 plus V1 square by 2 plus GZ1 is equal to P2 by rho 2 plus V2 square by 2 plus GZ2, right? And if I consider Z1 and Z2 are same, I will just drop this out, and we know V1 equal to 0 at this place. So what happens? Uh, but P1 minus P2, right? Density, let's say incompressible in this during the injector, so it's going to remain same. So P1 minus P2 divided by is going to be V2 square by 2, right? So this is going to be nothing but delta P by rho. There is V2 is nothing but Vox, which is going to be 2 times delta P divided by rho into square root. Say if you substitute it here, rho of oxidizer, A of oxidizer into square root delta P divided by rho of oxidizer. This you can rewrite it as area of oxidizer into 2 times delta P in the oxidizer orifice and then right. This is how we will write, right? So this is the formula you might have derived while following the lectures also, right? Did you guys understand how did I arrive at this formula?
Yes.
We just did Bernoulli uh, equation, right? But you should understand the Bernoulli equation uh, may not be more accurate in this place. So there will be uh, this separation happening, reattachment happening. All these things will happen in the orifices, and your exit area is going to get reduced, right? So to account for that, what we did, we multiplied with a factor, right? Which we call it
Coefficient.
discharge coefficient.
Okay.
So this is just to account for the irregularities in the flow while inside the orifice. Okay. Um, so we understood that we can find the mass flow rate of oxidizer inside a single orifice. This is single orifice, nothing but CD of orifice, area of orifice into square root of 2 into delta P of orifice, and then oxidizer orifice, and then row of oxidizer. So I think all of this is given. I think CD is going to be um, what is CD? Coefficient of discharge, which is 0.75, and then area of oxidizer is going to be pi by 4 into d oxidizer the whole square, where d oxidizer is nothing but 1 mm, 0.001 square, right? And then square root of 2 times what is the gradient of pressure gradient here? 0.25 megapascals. So 0.25 into 10 power 6, right? And then density is going to be 1200 kg per meter cube. This is the mass flow rate through single orifice. How much are you getting?
0.0144.
Okay, 0.044, which is kg per second. This is the mass flow rate through single orifice, right? Single orifice. Now, similarly, mass flow rate through a single, or let's calculate the number of so orifices in oxidizer injector. The mass flow rate of the oxidizer is already given, which is 1.44 kg per second. Now, if we want to have 1.44 kg per second, we need to have how many orifices? It's going to be 100. Yeah. So 0.0144. So it's going to be 100 orifices.
Where did you get this 1.44 kilogram per second? Is it given?
It's given. The total oxidizer flow rate is given,
Okay, okay.
right? The total fuel flow rate is also given. Okay. All right. Now let's find a fuel injector. So sometimes you need to note that you might get decimal values for this number. So, but you cannot have uh, decimal number of orifices, right? So you need to round off to nearest integer, and then okay. So fuel injector. Similarly, we need to find fuel's mass flow rate. So we will take this already derived equation, area of orifices of fuel to square root of 2 times delta P of fuel and density of fuel. Okay, so what is CD? It's going to be 0.7 pi by 4 times 0.85 mm square, so it's 10 power minus 3, right? And square root of 2 into pressure gradient is going to be 0.15 megapascal. Then the fluid density is going to be 1000. Okay, Shh. Are you getting?
6.87 into 10 to the power minus 3
6.87 into 10 power minus 3
meters
kg per second. This
kg per
is
second.
also again through one orifice. Now the total mass flow rate is nothing but 0.48 kg per second. So how much number of orifices we need? Mass flow rate of fuel divided by mass flow rate I F.
70.
So we need 70 orifices. So that's it. This is how you will calculate how much number of orifices present or how much number of orifices we need while you are designing the injector. Okay, so this mass flow rates, how do you get it? It depends on your mission and it depends on how much pressure and temperature you need to reach or how much thrust you need to get from the rocket. Based on that, you will design the mass flow rate of fuel and oxidizer. And once you find the mass flow rate of fuel and oxidizer, you have to select an orifice, and that orifice has the discharge coefficient, and based on the length it's going to have the pressure drop. And using this data you need to design your orifices. That's all. So that is how you do it. Okay, so do anyone have any questions in this?
The CD discharge coefficient has to be determined experimentally, right?
Yeah, so discharge coefficient has to be determined experimentally, true, because a lot of things can happen within the orifices, or you can even run CFD simulations, DNS simulations to find out, but experiments
Okay.
would be better. Yeah.
Okay.
So the pressure difference, right, in between the manifold and where it is getting injected. So is that solely due to the design of the manifold, or what are the other factors that contribute to that pressure?
So, the pressure gradient is due to the shear stresses or viscosity of the fluid. So, in order for the fluid to um, so let's say the fluid has to flow from uh, stage 1 to stage 2. So if the fluid has to flow, okay, so this can it can be opposed by the shear stress, right? So if you want the fluid to flow from here to there, you should have a driving force to move the fluid. So that driving force is the pressure gradient. So anywhere wherever you are seeing a fluid flowing, there is either there should be some force acting on the fluid in order for the fluid to move, right? I mean from rest to motion. So that force is pressure gradient, and that pressure gradient is needed in order to drive the motion here. Okay, uh, it has you are right. It has to do with the design. Uh, if your orifice is smaller, you are going to have a you may need a higher pressure gradient or you may need a lower pressure gradient. It has to it has lot of effect on the design of orifices too. Okay, that is simply due to lot of fluid dynamics happening within the orifice. That is the reason it depends on the um, design of the orifices. And shear stress is one of the important factor. And if so, whatever um, so the fluid can be acted by various forces. One is gravity, the other is uh, pressure, right? And the internal resistance offered due to the motion is what the shear stress. And if the other forces are not acting, so these two has to be balanced. The pressure and shear forces has to be and the inertial forces has to be balanced in order for the flow to happen. That is what happens everywhere. Okay.
Okay, thank you.
All right. If there are no more questions, let's solve the second problem, which is the gas generator cycle. Okay. So you all know what is the gas generator cycle. So there's going to be um, fuel and oxidizer tanks, and there's going to be pump. Maybe I will draw it. So
So one question, Mr. Dani, there
yeah,
was
yeah.
one more part of the problem in question number one, right? Like which
Oh,
is
yeah, yeah,
uh,
yeah.
mixture ratio.
So I thought you guys can easily
So
figure out what is the
yeah,
mixture.
so that would be just this 1.44 by 0.48.
Yeah, exactly.
Okay, okay.
Sorry, I missed it. So what is the mixture ratio? Is nothing but mass flow rate of fuel. Sorry, mass flow rate of oxidizer by mass flow rate of fuel, and it is going to be. I believe this is 3. You guys can check. Okay. Yeah. So all right. So now we have a gas generator cycle. Okay. And there is this fuel tank and there is this oxidizer tank. Okay. These are tanks. And what comes next?
Pumps.
So we need to. So the some pressure. We need to pressurize the fuel and oxidizer. So what we need is we need pumps. Okay. So how do we draw a pump? And similarly here also we need pumps. You need to give work to the pump in order for it to pump. Then you will take the so fuel and oxidizer is going to go. And then what comes next? So there is this pumps.
Injector.
Okay. Basically combustion chamber, right? So injector is leading to the combustion chamber.
Yeah.
So you will put it inside the combustion chamber. Then you will expand it through the nozzle, right? So there's fuel and oxidizer. Is that it?
Yeah, there should be a turbine as well,
Okay. Turbine is there.
driving the pumps.
Turbine gets power to drive the pump.
I think a portion of the fuel is actually injected through a gas generator,
Okay,
which
there is
powers
gas
the.
generator. Some portion of fuel is going to the gas generator. Okay. And what happens?
So the output of gas generator basically powers the turbine.
Okay, it goes into the turbine, and then there is some gases going to come out of turbine. So there is something problem with gas generator itself. Is fuel is enough for a gas generator to produce gas?
No, oxidizer also.
Yeah. So what happens? Chemical reactions is going to happen there also in gas generator, right? So there's going to be fuel and oxidizer get mixed in the gas generator, and it's combust, and the temperature is going to be high, and then that temperature, the high energy gas is going to drive the turbine, right? What happens to the output of the turbine?
It powers that both the pumps.
Yeah, work output powers both the pumps, but what happens to the outlet of the turbine? What happens to the
Okay, we can
gases?
feed it back into the main combustion chamber for added thrust, I guess.
Okay, but we are talking about gas generator cycle. If you feed it back, what happens? Will it be a gas generator cycle?
Okay, no, we have to exhaust it directly.
Yeah, exhaust through the aux nozzle.
There's going to be auxiliary nozzle here, and it's going to exhaust it outside. So you need to understand few things here. So we need to pressurize the fuel and oxidizer from lower pressure to high pressure, and for that we need power. And that power, we cannot carry a battery or something, and we can drive a motor so that we can give power to the pump. That power is going to be very high. So we should be able to somehow generate those power while we were in the operations, right? So that's why we have this separate uh, turbine which runs the power, provides power to the pumps. Okay, and you should note that if the turbine has to operate, what is required? What does turbine does? What is the
It
energy?
it expands the flow and extracts work from the flow.
It expands the flow and extracts work. So, um, uh, what is the energy conservation happening here?
Means it is converting the pressure energy or the potential energy of the flow into the mechanical energy of the shaft.
Right. So actually, what happens is it's not potential energy. So you should have very high temperature, not very high temperature, but you should have a temperature such that turbine can withstand. So you cannot have very high temperature also. But if you, because your turbine, the materials of the turbine is important, right? The material of the turbines can handle only, let's say, 800, 1800 Kelvin. Then your temperature can be, it can reach maximum to 1700 or 1800 Kelvin. Okay, so what it exactly does is it converts this thermal energy in the gas, right? This thermal energy in the gas, and then it converts into a mechanical power output. Okay,
Okay.
through thermal energy or pressure energy, whatever you said, but it's uh, uh, reduces. So this is going to be at high pressure, right? The pressure after the pump, and that pressure is going to get reduced to a low pressure, and while doing so temperature also reduces, and then by during this process it's going to gain some uh, work. Basically there is an internal energy change of the fluid, which is driving the uh, which is giving power to the turbine, and turbine is running the shaft of pumps. Okay, and
For the turbine, that input and output, should it be like in a different location? The input should be on the smaller cross section, right?
oh, okay, yeah, that is true. So because you are expanding it, it should be, yeah, true. So it should be here somewhere, and then it should be taken from the true. So whatever the work produced by the turbine should be equivalent to the pump work required. Okay. So yeah. So if you combine this two here, what happens? It will be a um, and uh, let's say you have a combustor here, right? If you combine this two, or if you take the output of this turbine and if you give it to the pumps, what happens? That cycle. So there is a pump,
A
there is a
staged
turbine.
combustion.
It's not. I'm telling that if you give it to the pump, not to the combustion chamber. So if you take this and give it to the combustion chamber, then it becomes a stage turbine, right? Sorry,
Oh,
staged cycle,
combustion
stage
cycle.
combustion cycle. Yeah. Here, this is the gas turbine cycle, right? So did you guys study that in thermodynamics? Brayton cycle.
Yeah, propulsion.
Yeah.
Jet
So,
propulsion.
so what happens? There is going to be a pump and there is going to be a turbine, and in between there is going to be a combustion chamber, right? Or constant pressure heat addition. Maybe you might have the process might you might remember it like that. And this high temperature outside of the combustion chamber is going to be going to the turbine, and turbine is going to expand, and then it's going to give it back to the pump, right? There's going to be some other thing here.
Yeah, that extracts the heat. Heat exchanger, I guess.
Exactly. So here you added the heat, here you are extracting the heat, right? So that's because you made it as a adiabatic expansion, constant, adiabatic expansion, right, in the turbine. It's going to be. Anyway, so that is not our interest. So this is the gas generator cycle. It's going to be, there's going to be, you're going to bypass fuel and oxidizer line into the gas generator, and you are going to do some, you're going to generate some gases, and you are going to give it to turbine, where turbine runs and takes the energy out of it, and then you send it to auxiliary nozzle to remove remaining energies also. It's for and it lets out to the ambient. Okay. So this is the gas generator cycle. Let's see what the question says. In a liquid propellant rocket utilizing gas generator cycle, the bypassing the main combustion chamber to produce hot gases under fuel rich conditions. So there it is a fuel rich condition inside the gas generator. The hot gases expand in the turbine, which drives the fuel and oxidizer pump. Okay. The exhaust from the turbine is further expanded in the auxiliary nozzle. So it's just explaining what is gas generator cycle. The pressure in the fuel and storage tanks is 0.5 megapascal. Let's say that this is going to be 0.55 megapascal pressure here, and in the oxidizer um, storage tanks it's 0.55 megapascal. The propellants are delivered to the main combustion chamber at a pressure of 7.1 megapascal. So the combustion chamber pressure is 7.1 megapascal. You can write it as PC or something. Okay, and the overall mixture ratio is given, which is 3.1. I believe. Let's write it out. Mixture ratio is 3.1. The overall ratio of mixture, okay, not the the supply mixture ratio. The densities of the fuel and oxidizers are also given, which is 800 kg per meter cube oxidizer is, and then fuel is 1000 kg per meter cube. Combined efficiency is given, so they gave a combined efficiency of both turbine and pump to be 0.82, the temperature of gas generator's outflow. So this temperature here, the temperature here is going to be 750 Kelvin. Is it okay? This is turbine outflow, right? So
Yeah, yeah.
they are telling
Input.
gas generator here. So it's outside here, right? It is going to be 750 Kelvin. Then the specific heat of gas from the gas generator. So they gave some specific heat out of the gas generator, which is 1900 joules per kg Kelvin. Okay. And then we have specific heat ratio that is also given, which is 1.33. Fine. The gas generator exit is connected to turbine inlet, and the fraction of total mass flowing through the gas generator F is 0.015. What is this? Fraction of gas generator divided by total. Fraction of mass flow rate to the gas generator um, from the total is what F is. It's given by F. Okay. The fraction of total mass flowing through the gas generator is 0.015. Alright, so we were asked to find the pressure ratio across the turbine, the ratio of pressure of the hot gases from the gas generator exit to the pressure of exhaust gas from the turbine exit. Okay, so um, so across the turbine you need to find the pressure ratio, hot gases from the gas generator exit and exhaust from the turbine exit. So across turbine you need to find the pressure ratio. Um, that is going to be, so that pressure ratio is required to run both the fuel and oxidized pump. So you have to expand to that pressure ratio in order to run both fuel pump and both the pumps. Okay, so the you are asked to find what is that pressure ratio. So how do we do it? Given data, we need to find. We'll come to the second question later. Pressure exit of the turbine and pressure inlet of the turbine, or vice versa. Pressure inlet is going to be higher, right? Say RP. This is what you need to find. How do we find it? Any thoughts?
From the work output
Okay.
of the turbine.
How do we find the work output of the turbine? We don't know work output. We just know temperature at the inlet of the turbine. There is some thoughts. Okay. Work output.
We know the temperature at the exit of the turbine.
We don't know that.
It's not ambient.
It's not ambient. Yeah.
Okay.
So what is the work output of the turbine? Do you know any relations?
Uh,
Start with that.
pressure gradient into the volume flow rate.
You mean RP times Q dot?
No,
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 not
no.
pressure
Pressure
ratio,
gradient.
pressure
Okay.
gradient, delta V.
Times volume flow rate. So you are doing the opposite of pump, right?
Yeah.
Okay. But there are more elegant uh, expressions also. It's fine. We'll start from here. Actually, professor already derived this relation in the class. I can give you the relation, but I do not want to because you need to understand how that relation came. Okay, so there is um the efficiency associated with turbine, right? You need to account for that efficiency here. How do we account? We can have a start. We can start from here actually. So how do we? Should we multiply with efficiency or should we divide it by efficiency?
Multiply.
Okay. So then, do you know how much work we need from the turbine? So what turbine has to do?
It has to drive both the fuel pump as well as the oxidizer pump. So if we can find out the power required by both the pumps, then we
Right.
can sum it together to be equal to WT dot.
Okay. So let's write WP to be the power required from both the pumps. Okay. So how do you write that?
Again, same delta
Okay.
P of the pump actually, and then Q of the pump divided by eta of the pump.
Okay. This is for just the oxidizer and similarly the same thing for fuel, right?
Right.
Is it right? But here there's going to be the pressure gradient is going to be same. So what we can, not the pressure gradient, the pressure difference. Okay. So the pressure difference is same and efficiency also same. Okay. Efficiency of pump. So what happens is it becomes the total mass flow rate. Sorry, volume flow rate, right? You can write it like this. Now this is the amount of work need to be supplied by the turbine. So from where turbine is getting the power?
From the gas generator. But one thing that I'm a little confused is why is the volume flow rate considered to be same for both?
It's not same. I'm writing total, which is Q of
Oh,
oxidizer plus
okay,
Q
okay,
of fuel.
okay.
Okay. So Q of total is equal to Q of oxidizer plus Q of fuel. So we know the work done by turbine should be equal to delta P by eta P. This is from tank to chamber. Yeah. Times total volume flow rate. This is the uh, work done should be delivered by the turbine. Okay, this is something should be delivered by the turbine, right? Now, how does turbine get the work? This is work output of the turbine. Now, how does turbine get the work?
From the thermal energy of the gas generator cycle.
Exactly. So, uh, how can we write that? Can we write it like this? Cp delta T, right? That is the energy lost by
Yeah.
the uh, gases in the turbine, and that should be equal to the turbine, right? So is this clear? It's just energy conservation. You just need to do energy conservation. You can arrive at this from the uh, first law of thermodynamics. The delta E is equal to Q plus work done, right? So here we are considering turbine to be adiabatic, and from there only you will get this relation. All right. So
When we say combined efficiency, does it mean eta P is equal to eta T is equal to 0.8?
it's not like that. It's combined efficiency. It can be. Each efficiency can be different. So ideally, what you should have done is there should be some efficiency with this, right? Efficiency of the turbine, and when you multiply these two, it's going to be one single efficiency. Okay, eta p times eta t will be the combined efficiency. Multiply eta p times eta t is going to be your combined efficiency.
Okay. So, like if there are two stages of the turbine and
Mm-hmm.
each stage has, let's say, eta T I, then it will be eta Ti multiplied by eta Ti overall efficiency.
Not exactly sure. I think most probably it should be. So you
Actually,
can,
there,
you
yeah,
can do it like this. So this is eta I, right? Eta I of any stage of turbine is going to be, how do you define efficiency?
actual
Done
work
by
of,
that stage divided by uh, the thermal energy change, right?
right.
In fact, in gas turbine cycle, it's going to be heat input in the chamber, right? So anyway, and if you want to find the combined efficiency or the overall efficiency, it's going to be work done by all the turbine divided by total energy change, right? So now you can divide it by work done I of DEI is going to be work done of I, summation of I, work done of I divided by summation of delta E I. This could be, this can lead to some expression of eta i's, right? You can
Like,
derive your own
okay.
combined efficiency based on the definition. It depends on definition of the efficiency also.
So in this
In the
particular question, combined efficiency, does it mean that 0.8 is the efficiency for the pump as well as the 0.8 is the efficiency for turbine?
you no need to do that. That's what I'm trying to say. In this analysis, there's going to be only one turbine and one or two pumps, but two pumps are going to act on the same pressure uh, difference, right? So you can see it as a one pump with the same pressure differences. Uh, the two pumps basically have different mass flow rates. So you can actually combine these two efficiencies and you can say that overall efficiency is 0.82, which means that you need to consider one efficiency only once, and that can be anywhere in between. So something like this is the so if you take this eta p to here eta t, you can replace this both efficiencies, you can replace it with one efficiency, which is going to be the representative of the overall efficiency. So here you can multiply eta p and eta t with your combined efficiency.
Okay, and that is what is given.
This is what is given.
Okay.
All right. Now how do we find what to find here? So let's see what and all we know. We know delta p, right? So because chamber pressure is given, the fuel tank pressure is also given. You know the delta P across oxidizer. I mean across the pumps, right? And the mixture ratio is given, right? So you can find the Q total. Uh, the mass flow rate of Gg, which is actually given as F, which is m dot by m total. Okay. So basically, you can take this Q total on this side, or you can write this as mass of how do you write mass flow rate of oxidizer times density, right? Mass flow rate by volume flow rate, sorry, divided by density. divided by density of oxidizer plus mass flow rate of fuel divided by density of fuel, right? And you know mass flow rate of oxidizer plus mass flow rate of fuel is nothing but total mass flow rate. If you rearrange this, you can bring this total mass flow rate in here, and you can replace that m dot gg in terms of just f. Okay, and then this cpg we know t in. Only thing we know efficiency also. Only thing we don't know is t exit. And if we find t exit into the uh, we know T in and we know T out, when we know it is an adiabatic process, so we can find the pressure P1 by P2 pressure ratio we can find, right? Is this clear what I'm trying to say?
Yeah. So this pressure ratio itself is the input to the turbine, pressure at the input to the turbine divided by output, right?
Right.
Okay.
This is the pressure ratio. That is what we need to find out. So what you have to do is you need to do these operations. You need to rearrange things. You can actually, since you want pressure ratio, you can take t in outside. So since t in we already know, we can take t in outside, then you can minus 1 minus t exit by t in. And from adiabatic relation you can replace it by p exit by p in, or p in by p exit. So there will be that gamma minus 1, all those relation will you need to incorporate. If you do all of these, what you could do is it's just energy conservation, but you can write this in terms of like this is the relation given by professor. Actually he also derived this, so I'm just giving you the relation here. So it's nothing here. We can, since we know oxidizer by fuel ratio. If you take a mass flow rate of oxidizer here, then this becomes divided, so it becomes R here. That is what you see here, R. And then similarly, okay, you take fuel outside, because oxidizer divided by fuel is mixture ratio. Since we wrote MR, we'll stick to with that MR. Okay, and then that's what you see here, times delta P you see here. And then you have this efficiency which you brought down here, so that efficiency is here. And this m dot cp is here, and cp is here. This m dot has changed into 1 plus r. You can do this calculation and you can see how it changes. And then similarly this part changed into 1 minus 1 by rp power gamma minus 1 by gamma. So this is the equation you need to solve for to get the R. Okay. So basically it came from energy conservation. How much energy you need from the turbine is equal to the internal energy change of the, or the enthalpy change of the uh, product of gases across the turbine. Okay. So from there only this relation came. Okay. And we just need to plug in the values and get the results. So what we need is we need to find this rp. So maybe I will put, can write this as eta times 1 by r 1 plus r cp times t gg uh, rp power gamma minus 1 by gamma equal to delta p by f 1 by rho f plus mixture ratio divided by rho oxidizer. So you can this down, right? Because we know everything from here. You can rearrange this. This would be written as 1 by Rp power 1 minus P. Then, yeah, basically you need to rearrange to this calculation. So Rp power gamma minus Tp Tgg divided by 1 minus delta P by F mixture ratio times divided by rho oxidation. That's it. So since you know everything from here, you can just simply substitute and get the results.
Is the minus one minus only on the numerator or was it in front?
I'm not sure. This is the relation we have. I just rearranged it. Did I make any mistakes while rearranging?
Can you go back to the third step from bottom?
Okay. Is this
The third one from the bottom, third
this one?
equation. Yeah, yeah.
Okay.
So we are rearranging. So 1 by Rp is going to the right. So this
This
entire ratio 1 minus from actually from third to the second last. How is that transformation
this
happened?
one.
Yeah, I mean 1 by Rp to the power gamma minus 1 by gamma. So you are taking this entire right side
Yeah.
one minus this entire right side thing, right?
So I just took this denominator on this side. Okay. And took this f on below. Okay.
No, no, that one is okay.
Okay.
Please go to the last second. Yeah, last second.
Ah,
That
okay.
is, yeah, it
So
is one minus the entire thing, right? Not just the numerator, but the
yeah, yeah,
entire
yeah,
thing.
yeah. Sorry, sorry, sorry. It's one minus the entire thing. Yeah, you're right. Um, it's like this, and then you can rearrange it. So it should be Rp power gamma minus 1 by gamma is equal to 1 divided by 1 minus delta P by F 1 by rho F mixture ratio by rho of oxidizer divided by eta times 1 plus R CPT GG. Okay, fine.
Yeah, now it's fine.
So you just need to substitute in this relation and you need to get this results. So let's say if I start substituting, it should going to be delta P. How much is delta P? 7.1 minus 0.55. It's going to be 6.55 megapascal, right? So let me just substitute it 6.55 megapascal, which is going to be 10 power 6 divided by 0.015 times 1 divided by rho of fuel, which is 1000, and mixture ratio is some 3.1, I guess, and divided by 800 divided by efficiency 0.82 times 1 plus 3.1 times 1900 times 785, I guess. 785, 750. Okay, 750. This is going to be Rp power gamma minus 1. So then you can rearrange it to be is equal to this whole term gamma by gamma minus 1. Then you can find Rp. Can you guys quickly find it? Gamma is 1.2 3 3. So why I could have started with this relation, but why I did this is in order for you to understand uh, the energy conservation is giving this formula, so that you will appropriately apply this conservation for whichever the cycle you have. Let's say stage combustion cycle or extended cycle. I think it's extended compression cycle. Something. So basically, everything comes from conservation principles. That is what I need to tell here. All right. Did anyone get any answer? How much is RP?
Is it 1.25? That's too low.
You are getting 1.25. Did you
Yeah.
do this gamma by gamma minus 1 also?
Oh, sorry, I mixed. Okay, that entire thing is 1.25. RP to the power gamma means.
You are getting 1.25. All right. I am getting 1.7 to 1.8. And which you are getting?
Is the combined efficiency point 0.8 or 0.82? 0.82.
0.82.
Okay.
Mm, it's 0.82. This is going to be pressure at the exit of the turbine. Sorry, this is going to be pressure at the inlet of the turbine divided by pressure at the exit of the turbine. So anyway, we need uh, pressure ratios, so we can find it by this. By the way, this is not division. I'm just could be any of this. I'm just all right. Did anyone get the answer? Pressure ratio.
It's coming out to be too less, 2.45.
You got 1.25, right? 1.25 power 0.3. You are getting 2.45. Okay, yeah, it looks like it's too less. Do check the calculation once. Okay. So I'm getting 1.8. I calculated.
Okay.
Uh, you can check it back again. Anyway, this is how you need to find the pressure ratio. That is important. And then the second question is, the net specific impulse of a system is 2960. Okay, this is the specific impulse of this entire cycle. And if the specific impulse of uh, main combustion chamber nozzle system, this specific impulse is 3000 seconds or 3000 meter per second. The specific impulse of auxiliary nozzle. What is the specific impulse of the auxiliary nozzle? So we have two nozzles, right? This there is this nozzle and there is this nozzle. So in both the places we are going to get some thrust. So specific impulse also depends on both the nozzles. Okay, and we are what has been given is the specific impulse of the system, whole system, is 2950 meter per second, and the specific impulse of the main combustion chamber nozzle is 3000 meter per second. What is the specific impulse of auxiliary nozzle? It's just 3000 minus 2950? No, right?
I think we should consider the fuel fraction.
Why should we consider fuel fraction? How should we consider both the questions, how and why? You are right, actually. You should consider fuel fractions. But why is it coming?
Because so the fuel fraction that comes to the combustion chamber, right, which is CC in, that would be 1 minus the fuel fraction which is going into the gas. So 1 minus that.
Right. So basically, you are telling we should weight this by fuel fraction,
Correct.
right? So uh, it is going to be total ISP minus 1 minus F times ISP of CCM, right? This is what you are telling, right? Our total ISP is F times ISP of auxiliary nozzle and 1 minus F times ISP of main combustion chamber. This is what you are telling, right?
Correct, yeah. But I don't know if it is
Sorry.
minus.
Okay, there's going to be F here, right?
Yeah, yeah, yeah.
So
Yeah.
basically, what you are trying to say is, maybe I will write it like this. So F times ISP of auxiliary nozzle plus 1 minus F times ISP of combustion chamber, main combustion chamber and nozzle, right? This is what you are telling.
Correct, yes.
So it is right. This is the equation we are going to use. But we should know how this equation came. Why should we multiply by mass fraction or fuel fraction?
Can we connect this? Can we get this directly from the mass flow balance? Total mass flow rate is equal to mass flow through the main combustion chamber plus the gas generator, which is actually the mass flow through the auxiliary nozzle.
Right. It's actually coming from there. Uh, so basically, what you know is, so let me write it down. This is nothing but total mass flow rate divided by, sorry, what is ISP? It is coming from definition of ISP. It's so simple. It's going to be the thrust divided by total mass flow rate, right? What do we know about thrust? Thrust is going to be thrust of combustion chamber nozzle plus thrust of auxiliary nozzle. This is true, right? So let's say if you substitute it here, the ISP, this is the total ISP of a system. Let's say if you substitute it here, what happens? Combustion chamber of nozzle divided by mass flow rate, total mass flow rate, plus the uh, what is this, auxiliary nozzle divided by total mass flow rate. And what we know about combustion chamber nozzle's thrust, it is going to be ISP of combustion chamber nozzle multiplied by mass flow rate through the combustion chamber and all that, right? You just need to substitute it
Yeah.
here. It's again coming from, as you said, it partly comes from mass balance. You can also derive it through mass balance, or you can just say my net thrust is going to be thrust of auxiliary thrust produced by auxiliary nozzle plus thrust produced by the combustion chamber, the main nozzle, right? So if you do that, you are going to again get the same results. So if you just substitute these two here, you are going to get m of to the combustion chamber main combustion chamber nozzle divided by total into ISP of this combustion chamber nozzle assembly plus m dot of an divided by m dot of total, which is, we know, auxiliary nozzle is nothing but GG, right? Gas generator, which we know is F multiplied by ISP of the auxiliary nozzle. And if this is F, this is going to be 1 minus F. So that is how you arrive at this equation. So what we need to know here is auxiliary nozzles ISP, which is going to be ISP of total system minus 1 minus F of ISP of uh, main combustion chamber nozzle divided by F, that the F comes down. Okay, so let's substitute it here. 3000 minus 0.015 times combustion chamber. Oh, sorry, this is 3000. This is not 3000. This is 2950. Yes, do you have any doubts? Is this clear? How did we arrive at this?
Yes.
So basically, this is how everything gets arrived.
So one question. So this 2950 and 3000, right? So does it mean the gas generator cycle is reducing the overall specific impulse of the system?
I think there is a problem with the numbers I gave. Raise the specific impulse, it cannot reduce it. So it is. Oh, okay, okay. So it will have its own. Uh, so so it has to do with, this is 1 second. This is not 50. This is 60. Let me make this correction. So it 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 does reduce the overall specific impulse. It's simply because you are dividing the mass flow rate. Okay, so if you would have given the whole mass flow rate to the combustion chamber, you are going to get 3000. But what you did is you took some of the um, uh, some of the masses from the combustion chamber and you are giving it to the auxiliary nozzle. So what did auxiliary nozzle didn't expand it more efficiently, so that gave us less specific impulse. So this is like a compounding effect. You have a you if you would have given that mass flow rate to the main combustion chamber, you are going to get higher specific impulse, but you divided it and gave it to a lesser efficient system. So overall specific impulse should come down, right? In that way.
Okay, okay.
Okay, so the what you should know is, if you would have given the total mass flow rate to the combustion chamber, you are going to get 3000. But what you did is you took it and gave it to an inefficient system. So you have to face that penalty, right? It's like uh, the resistors in parallel, right? In series you will just add it up. In parallel you will do one by thing, but what happens, the resistor will actually reduce, right, than it has to be. If you do a serial connection to that, it will have a higher resistance. When you do a parallel, it comes down, right? You can think of in in that manner also. Uh, you are just you just divided the mass flow rate. That's all.
Okay.
Face that penalty. Instead of giving into a high efficient system, you gave it to an inefficient system. So that penalty is what we see in terms of ISP. The overall ISP of the system goes down.
Is it also the reason why actually staged combustion is more preferred compared to gas
Exactly.
generator?
Yeah. So in stage combustion, you do not have auxiliary nozzle. Instead, you give it to the main combustion chamber, and that is going to be more efficient. So the total mass flow rate is still in the uh, uh, main combustion chamber. But yeah, that is true. That is true. But you should note that you took some power from the gases, and you have so that work has to go somewhere else, right?
Right.
So the initial energy the gases had before entering the combustion chamber will be reduced slightly because some gases you took and used it for your work, right? So in that way it will affect the uh, maybe it might reduce the chamber pressure by a little bit, or it might reduce the chamber temperature by a little bit. In that way ISP get affected, but that is different. But if you just see in terms of the cycle and how it is if you just see the nozzle part, this is going to be more the stage combustion is going to be more efficient.
There was also a thing called gas-fed liquid propulsion engine, right? There was
Yes.
something I don't remember exactly. There was something in which the gas is pressurized by another gas, like a inert gas. Could
Yeah.
you please shed a little light on that?
So I think those are all. I don't know whether they're using it right now. I'm not sure exactly. Um, but it's just the pressurized gas is going to. Uh, it's called blow down cycle,
Yeah,
right?
yeah, yeah,
Blow out or blow down
yeah, yeah.
cycle.
Something similar. Yeah.
Huh. So what happens is there will be a high pressure inert gas. This will be at very high pressure, and you are going to have a fuel and oxidizer tank. And what you do is you supply this inert gas here, okay, and there will be some diaphragm or something which separates these two. So this high pressure will come and hit this piston or diaphragm, and it moves down, which pressurizes the fuel and oxidizer in here, and this directly gets into the combustion chamber. uh, this directly gets into the combustion chamber. In this way, the pressure won't be uniform. In pump, you are going to uniformly give, let's say, if it's 7 megapascal, you are going to give 7 megapascal throughout your entire operations. But here the pressure will vary because the pressure here is going to keep on reducing as it pushes the fuel and oxidizer out of the cylinder. So in that way, the pressure keeps on going down, and that is the reason. I don't know whether it is preferred or not. I'm not sure. It's most probably
For
not preferred.
small rockets, I think it is used, but not for larger.
Maybe smaller, yeah, because you don't require pumps, and yeah,
Yeah, exactly.
it depends on where you are. So this is clear, right? How do we get ISP?
Yes, it's clear.
Okay. So now we completed both of the questions. So this is how you need to solve. So in your assignment, there's a different cycle, a regenerative expanded cycle like this. So want to solve such problems because it would be easy and you will just follow it. I want you to learn from this and want you to apply the concepts and then arrive at the results. So okay, um, this that's all for today. If you have any questions related to previous week's assignment, or any course related doubts, you can ask me now.
Yeah, please go ahead.
Yeah, go ahead, Kapil.
No, no, you go ahead.
Okay, thank you. So, yeah, I had a question on assignment week number 8, assignment number 3. So
Okay.
that was, yeah,
Kate, assignment. Question number 3.
question number 3, yeah.
Okay, let me check. The value of A70 in millimeter per second. Okay.
Okay, so this one there is some confusion, Mr. Ganesh, in terms of how this pressure should be considered because, and there is also an active email thread or a discussion thread going on in our group actually.
Yeah.
So what I'm not still convinced is in the videos, right? Professor had explained that A70 corresponds to the value at pressure when the pressure is expressed in atmospheres, and A7 means it is when the pressure is expressed in megapascals.
Okay.
So, but in the solution, right? So the pressure considered here is in megapascal. So that is how the correct answer is given as 14.
I see. So,
So
yes, right,
if you
right.
have access to the discussion forum, can you please open that? Maybe it'll be easier to.
Yeah, I could do that, but before that, let me write this. So, this is so. Uh, uh, 1 second. Give me some time. So, RB is APN, right? So, at what are the things they give? They said that P is in megapascal, right? A70 means it's always at 7 megapascal. It has nothing to do whether it is A70 is just easy to express, so they expressed it like that. But according to 7 megapascal, what is the burning rate is what going to give you A70. Okay, so that you must be clear. So two strands of composite propellant when burnt at 2 megapascal and 3 megapascal. So again, pressure and RB 2 megapascal and 3 megapascal. This is given in megapascal. And what is the RB you get? It's 4 and 6, right?
Right.
This is mm per second and 6 mm per second. Sorry. So we know RB is AP power n, right? So what you want to find is A70. What is A70? What do you think A70 is?
So A70 would be P by P reference at 70 atmospheres to the power n.
Exactly. So it is nothing but RB is nothing. A70 is nothing but RB. I can write it P at 70 atmosphere. Right? Is this clear?
Correct.
Now, if you want to write RB at 70 atmosphere, you need to write APN. Okay, we don't know A yet. So P is in megapascal, which is given in the question, right? P is expressed in megapascal. Okay, so 70 atmosphere corresponds to 7 megapascal power n. Is this clear?
Okay, but this would give the value of A7, right, instead of A70.
Uh, only um, the A7 and A70 both are same. So if you express in megapascal, it's going to be A7. If you express in atmosphere, it's going to be A70. But A70 and A7 both are going to be same, right? Even though it has different names, it's going to be same, right? It's going all corresponds to 7 megapascal or 70 atmosphere.
Correct. So if we are mentioning A70, then we should retain the power, I mean the pressure in atmospheres, right? Like which is 70.
Let's forget A70.
Okay.
Okay, let's not worry about A70. Let's first find out what is A and N here. What is A and N? Did you find out?
Yeah, I think n was given as 1. That is given in the problem, I think.
Okay, n is given one.
Oh, no, no, we found it actually, yeah. The first question, right, where we found n. So n was found to be 1.
Okay. So and A is found to be, what is A? This is P at megapascal. Uh, this is 1. And what is A? Did you find
It
A
was found
also?
to be 2. Yeah, 2, 2.
Okay. All right. So this is your RB relation. Okay. This is fine, right?
Correct. Mm-hmm.
Now you were asked to find A70. And what is A70? RB at 70 atmosphere, right?
Correct. Uh-huh.
Or RB at 7 megapascal, correct? Both corresponds to A70. You can even write A7. Both are same only, right?
Okay, okay.
So if you just need to substitute in here. So if you according to 7 megapascal, it's going to be 14, and you should express this in millimeters per second. This is important. So it's going to be 14 millimeters per second. This is RB at 7 megapascal. And now you term this A70, A7, it's up to you. But whatever you term it, it's going to be burning rate at 7 megapascal or burning rate at 70 atmosphere. And that is always going to be 14 mm per second.
Okay, so the question was actually asked in two decimal places. So, and I think the little bit of deviation that came, right, was the conversion between atmosphere and megapascal. So I think one atmosphere is sorry, 1 megapascal
Okay,
is,
okay, okay.
so
Hmm.
it's, yeah, so there was little in Google, right, it was like showing as 1 atmosphere, sorry, 1 megapascal is equal to less than, little less than 10 atmospheres, like 9 point something or something like that. So the answer was asked in decimal. So when I gave 14 my answer came to be 14.19 or something.
So,
So
uh, okay, let's try to do that also. Let's see, I'm also getting the same thing. So, what you have to do is you need to convert this A P as a function of megapascal to A is, let's put it 2 power. This is your relation. So in order to find A70, you have to convert this into atmospheres, right? So what you have to do, you have to divide it by 110 power 6 in order to convert into pressure as a pascal. And then what you have to do, you have to uh, multiply by 101,325. Uh, how much was it? One pascal is equal to 325 be 1 atmosphere, right? You want to have um, change this to be how do you change megapascal to, so you should modify A also, that's what I'm trying to say. So let's see, trying to find out that RB P at megapascal, right? So if you want to change it to A, this is going to be which is nothing but meters per second per megapascal. You said you want to substitute in terms of atmosphere. So what you have to do is 2 into mm per second. Um, you convert megapascal to, so 10 power 6 pascal. You can do that. And then 1 pascal is going to be so 325 divided by 10 power 6 mm per second divided by atmosphere. Fine,
okay.
right? So A changed. A is going to be 2 into 101,325 divided by 10 power 6 millimeter per second divided by atmosphere. Now you have to find RB, which is 70, A 70 you want to find, which is going to be uh, this A modified, maybe we can put dash here, A modified times pressure, which is at atmospheres. And n turns out to be 1, that's why there is this n also gone away. Okay, so let's ignore this for a minute. And then now you want to substitute it to 325 to 10 power 6 into pressure is in atmospheres, so it's going to be
70.
70.
Yeah, so 14.185 is the answer.
14.185. Okay.
Yeah. So and they even in the question the answer, I mean, it's mentioned that the answer should be given in two decimals. But the solution key says only 14 is the correct answer.
I see, but
So this is the
it's,
same value even I got. So 14.19 is what I also put.
just by changing the units you shouldn't get a different answer. There's something we are missing here.
Yeah, I think the reason is because Pascal to atmosphere, right? I think generally we consider that 1 Pascal is equal to 10 atmospheres, which is why 7 is
Okay,
equal
okay,
to
okay, okay.
70 comes.
Right,
But
right,
that is,
right, right, right.
right,
So this 70 atmosphere is not equal to 7 megapascal.
not exactly, yeah.
Yeah, so 70 atmosphere is not equal to 7 megapascal.
I think that's why the difference comes.
Yeah, exactly. Hmm. This is asked to be A70, so you took, they were asking in terms of atmosphere, so you converted and found it. Okay.
Yeah, yeah.
What did professor say?
No, actually, it was being replied by Mr. Abdul.
Okay.
So that thread is still open actually.
Okay.
So if you can please help us figure out come to a conclusion, that would be great.
Okay. So, yeah, I will ask professor about it. Uh, this looks genuine. Yeah, this is true. A70. It's been asked A70. Hmm.
Because if the
Yes. Yeah.
question
Yeah.
was A7, yeah, you're right. Like 2 into 7, we can straight away put an answer would be 14.
Correct. A7. Yeah, that is true. A70 means you should. I don't know. You should put 70 atmosphere. You shouldn't put 7 megapascal. Right.
Correct, correct. So this minor difference comes when we are converting that pressure which is given in megapascal to atmosphere, right? So it is not a direct conversion.
Right. Okay. No problem.
I have one doubt related to assignment 11.
Okay.
Sorry, assignment 9, week 9 assignment.
Assignment 9.
Okay, so it is related to question number 24. It's all about monomethyl hydrazine and N2O4. So
Mm-hmm.
N2O4 is being pumped by a two-stage pump with
Okay.
a net efficiency of 0.7. That is what
Okay.
is given.
Okay.
So it is a two-stage pump. So I'm a little confused with this one. Like, should we take zero point 0.7 for each of the stages, and as a result, the overall efficiency is 0.7 into zero point 0.7?
No, so it is given net efficiency, right? Net efficiency means overall efficiency. They already did all those conversions and they gave you the net efficiency. So,
Okay, so it means that eta p1 into eta p2 is equal to 0.7.
yeah, it's not exactly into, I'm not sure whether it is exactly into or not. This total work done, or you can write it like, how do you write it? So the overall efficiency is going to be the total delta PQ dot divided by work given to the pump. So this work corresponds to both the stages, WP1 plus WP2. This delta P is actually both the stages gave you the net delta P what the pumps gave you. Okay.
Okay, let's say had it been given like separate, not net efficiency, but rather stage efficiency, how would the things change in that case?
So what is your interest? You need to find work done. No? So work
Yeah.
done of one stage is going to be delta P in that stage times Q dot, okay, and uh, divided by eta of that stage, okay, and then work done of second stage is going to be delta P of second stage Q dot divided by eta of second stage, okay. So if you are asked net work done, it's going to be delta P1 Q dot divided by eta P1 plus delta P2 Q dot divided by eta P2. This is how you find two stage
Okay.
network.
Okay.
So here they didn't give each stages how much you are having the pump, right? Like each stage how much it is pumping. It's not given, right?
Yeah, it's rather net efficiency.
Net change in pressure is given and net efficiency is given. The two stage pump is given in order to just say that it is a two stage pump. That's all. But the pump work is going to the you can see it as a one pump and you are going to have a uh, efficiency of zero point 0.7, and that is why it is defined as net efficiency in order to see you the two stage work two stage pump as one. Okay.
Okay. Okay.
Is there any other doubts?
So there is actually one more ongoing discussion about the calculating the web thickness because
Yes.
I think there is some confusion whether it should be divided by 2 or just the outer diameter minus inner.
So web thickness is thickness, right? So it should be how it should be. It should be just the R outer minus R inner, I believe. What is the discussion going on?
Yeah, so in the videos, right, the sir had mentioned that it is d0 minus di divided by 2 because
Exactly.
that will give the thickness of the one side because there are two sides in a cylindrical frame, right?
It's not two side, no. It's throughout the radius, throughout the uh, theta direction.
Correct, correct. So it is d0 minus di by 2.
Yeah, that is
Okay.
how web thickness has to be calculated. So it is you should not see cylindrical as only two. Okay, so it is throughout the this thing
Circumference.
Okay.
circumference exactly. So it should be r naught minus ri. That's what I think. That is how thickness is given for a hollow, let's say ring or hollow cylinder. The thickness is given like r naught minus ri. Right? Similar goes for web thickness also.
Okay, okay. Because in the in I think this question came up in 2 weeks actually. I think week 8 and week 9, and the solution file had mentioned it as du0 minus di.
I
And the
see.
answer, yeah. So that's where there was a confusion, and I think this is also a discussion which is actually still open in the discussion forum.
I see. Okay, I will look into that discussion. Maybe I will
Yeah.
ask
So okay,
about it.
assignment 9. I think week question number 6.
Okay, question number 6. Hmm. Centimeter. Okay.
The diameter is given, so it's zero point 0.2 minus zero point 0.1 divided by 2,
2.
right?
Okay. Okay. I will ask professor to look into it and maybe reply to you about it. Okay.
Yeah, assignment 9
9.
actually. Yeah.
Question 6. Is it? Question 6.
Uh, yes, question 6. Correct.
Any other doubts? Out in week 9, assignment 12 question. Okay. What is your doubt, Sham? Is it Sham or yeah? Characteristic time of combustion corresponding to burnout of a solid grain in milliseconds at one decimal place. So this should be straightforward, right? What is the doubt you have in this? In solution, they provide answer as 4.88. Okay, let me look. So you're not getting 4.88. Is this a problem with other people also? Kabir and Satish, Sri Lakshmi.
Yeah, I think little bit confusion is what the us is because in this problem, like both actual C star and ideal C star are given, or rather we found one. So wherever there was C star involved, at least I had that confusion on which C star to use, whether should use actual or ideal.
I have used most of the time the sister actual, and that has given me answers which are wrong. Like this, Shyam has written like 4.88, so my answer also got deviated from the actual answer.
Okay. So it depends on the characteristic time is defined. T by TCH is going to be V by gamma square C star. Right? So you are getting from square root of RT.
So what I
So you should I believe it should be theoretical C star.
But theoretical is gave me the wrong. It gave me slightly less out of range from what is the answer given. But if I put the actual star, it is coming to be a answer within the range in the set.
Actual C star is giving you the correct results, or theoretical
Yeah,
C
yeah.
star is giving you correct results?
Actual is giving the correct results.
The C star actual is giving correct results.
Correct.
Is it the same with Kabid also?
Let me see. I have to check it too.
So, what I believe is basically it comes from the relation, and it is nothing but V by gamma square C star, right? And you were able. Okay. So, trying. From this equation only you will be finding the SPAPN minus EAT by C star. So this C star is actual. That is clear, right?
Correct.
This C star is actual. Then you take C star outside. You took was AT and C star outside. So RT by V into AT by C. So propellant SPAPN AT minus P. This is what happened. So the C star is still actual. Made this to be V by 8. V by 80 is L characteristic.
Correct.
So RT by star C star, right, times this whole term. You said was this part is T characteristic. L star, how did
So,
where is
has substituted the value of R as gamma square theta square.
this as what is this?
Gamma square
Gamma
is
square
theta square. So,
square C star square. But this C star is
again,
theoretical.
yeah,
Yeah, you should be
we
careful
are
here.
left with one C star because the numerator denominator
You
cancels.
cannot do that, right? So wait a second. So this is going to be gamma square C star theoretical C star theory divided by L star C star times this whole term, right? What do you know about this is C star actual? So efficiency of C star efficiency is nothing but C star actual by C star theoretical.
Correct.
So C star actual is nothing but eta C star theory. Okay, so let's say if you substitute it there, you are going to get dp by dt is equal to gamma square C star theory gets cancelled, so it's going to be gamma. So there is a square here. Okay, so it's going to be gamma square C star theory divided by L star into efficiency of C star.
Hmm.
So now, what T characteristic?
It is the volume divided by the product of area of the throat gamma square into C star. I mean, that is the end result.
This efficiency coming in. So wait. So here gamma is this is so this is this whole term is meters. So gamma square uh, p star square times gamma star the whole square is RT, and so second, let me try. Let's find out what is T characteristic. Okay, what we know about P bar is going to be uh, P divided by P equilibrium, right? Similarly, T bar is going to be T divided by T characteristic. That is true everywhere, right? So this has something. Let me write this down also. Yes, P A P N C star. This is still actual. It's not theoretical, I believe, isn't it? Yeah.
Yeah.
And A T minus P, right? Uh, we need to do is we need to express P in terms of P bar and P equilibrium. And if we do that, what happens? D P bar by dt bar into P equilibrium by TCH, right? Because T is nothing but T bar TCH, and it's a characteristic. It is equal to gamma star theory divided by L star eta C star. Yes, B rho P A P bar power n C star. How did you replace this? The value was seen to be P
Yeah.
equilibrium. Huh.
I think the p to the power n is remains as it is, right? And everything other than that is p equilibrium to the power 1 minus n.
Right. So this is going to be P bar P equilibrium n. So what were you telling? This
Correct.
part, this part
Yeah.
is P equilibrium power 1 minus n.
Correct. Yeah.
Right. Okay. Mm. So yes, yes, B rho P A C star divided by AT is nothing but P equilibrium power 1 minus n, right? And if we do substitute that here, P equilibrium divided by T characteristic is equal to star theory divided by L star eta C star. So this is going to be is P A C star by AT is going to be P power n P equilibrium power n
One.
times P equilibrium power n, right? Minus P bar P equilibrium power n. Sorry, not power n. P equilibrium. So this is going to be P equilibrium, and which you can take out. So dp by dt times P equilibrium by TCH to gamma square C star theory divided by L star eta C star times P equilibrium into P bar n minus P bar, right? And this you can cancel it. You know dp by dp bar is nothing but p bar minus p power p square c star theory divided by l star eta c star tch, right?
What did we do in the last step?
So we know that by dt bar is nothing but p bar over n minus p, right?
Yeah.
This we know, no? So I just replace this with that. So I'm doing the opposite way. We need to
Okay.
find
Okay.
a t characteristic. So I'm doing the opposite way. Okay.
Okay.
So if you do that, it goes away. Ch is nothing but L star eta C star divided by gamma square C star theory. This is what I'm getting.
Yeah,
Don't
I think so what I think what the way I think it was we took notes was that efficiency, right? That term was missed out. So
okay.
it's just been noted as C star.
Okay, okay.
Yeah, so I think I quickly did the calculation now. So if we include that efficiency factor, the answer is coming to be within the range given in the solution, right?
How much are you getting?
So see, without the efficiency, I was getting 4.74, and by multiplying the efficiency of 0.95, I'm getting it as 4.98.
4.98. Okay.
So which is the answer is 4.9 to 5.1 is the correct answer.
Right. Okay, so let's see this. C actual by C star theory. Okay, C star theory can be replaced as, so we have C star theory. C star theory can be replaced as C actual by. Okay, yeah, this is the, I think this is the so if you find the characteristic time through this, are you getting 4.98?
Yeah, by including that efficiency factor, yes,
Okay, okay,
4.9.
okay. So
After all, this is we are using C star actual only, right? Because C star efficiency is there also, no, in the numerator.
no, C star efficiency is C
No.
star actual by C star theory
Yeah, so we are actually doing C star actual by C star theory twice, something like that.
square. Yeah,
Square, yeah, yeah.
yeah.
Okay.
Yeah, you need to follow this actually. The solution manual didn't have that, right?
No, it
They do
didn't have
not.
the
They did
steps.
not write the efficiency there. There's no steps also. Okay. So actually, you should follow like this. So basically, you should come back to where it had happened. So then you will be able to derive. Yeah.
Okay.
Any other doubts?
So will there be a separate some session for how to prepare for the exam now that we are close to exam time?
So yeah. When is the exam?
I think we have not got the dates yet, but it's sometime in the week of 28th April.
Yeah, there should be some sessions for revision. Most probably, I will be holding, and Nikhil also will be holding, I guess. There will be another two sessions where I will be helping in solving, and one will be for revisions, I guess. Most probably.
So exam also will be in the same format like assignments, or will there be like we'll have to write paragraphs, or is it all yes or no answers? What is the format?
I'm entirely not sure how would be the format. Uh, uh, you can ask professor about it. You can email in the discussion forum. I have no idea how the exam is going to be.
Okay, okay, no problem.
So questions? Okay. Thank you,
Uh,
Satish.
Could you please discuss a little bit about the variation of C star efficiency throughout the burn, from initial burnout, from the initial burning to the burnout?
Hmm. So, most probably, till what I have observed is uh, it is going to be C star itself is going to be almost constant throughout the book. Okay, so that's so I speculate C star efficiency is also going to be almost constant throughout the book. Okay, so it's
Okay.
till because m dot is also a variable, pressure is also a variable. So PC 80 by m dot is going to adjust itself, and it is going to give you whatever the efficiency. So that C star efficiency is actually has to do with the combustion chamber. Okay, the how efficient your combustion is happening. So it depends on if your combustion is happening more efficiently, you are going to have higher C star efficiency because you will have higher pressure buildup, or the pressure buildup which is depicted by the theoretical value. Um, but this pressure buildup, if you have if you increase the pressure buildup, the mass flow rate through the nozzle is also going to rise, right? So, and if you increase the pressure buildup, you're going to add more and more mass through. So this mass flow rate is also variable. Pressure is also variable. So most probably you are going to have almost constant C star efficiency throughout the burn, and that is
Okay.
going to depend on efficiency of your combustion. How efficient
Okay.
is your combustion?
This actually contradicts the answer given in question number 13,
Okay,
week 9 assignment.
what it says?
In practice, the C star efficiency at burnout comes to be different from the initial value.
Yeah, there could be an which one?
13.
Okay. The C star efficiency at burnout comes to be different from initial value corresponding to the ignition. Would C star efficiency at the burnout be more or less equal to the value at the ignition? Choose the correct answer. So, um, the C of the C star from ignition to burnout. So throughout the in the during the burn time, it's going to be constant, but at the ignition and burnout, you should think carefully. So uh, ignition, you are going to have pressure buildup inside the combustion chamber, right? So maybe you can use some of the formulas. Okay, so what are the formulas you have to find the pressure buildup inside the once you reach the equilibrium pressure, you are going to have almost constant C star, but until you reach the equilibrium pressure, you are not going to um, C star efficient to be same as whatever the equilibrium C star efficiency, right? Similarly, after burnout, you are going to drop the from equilibrium pressure to the lower value. Similarly, at that point also, there's going to be C star efficiency is going to change. Okay.
So when this question is asking, what this question is asking is it like corresponding to the ignition means at a particular initial radius, and then at burnout means at the last radius, I mean at the end of the burning. So both points are equilibrium points, right?
So ignition is not an equilibrium point, right? So
Okay.
ignition, first it will ignite, and then flame has to spread. That is the ignition. Once flame is spread, ignition is over. But there is this time for the pressure buildup, right, to reach equilibrium.
Okay. So at burnout means at the end of ignition or at the end of the total burnout of the grain.
So burnout be more or okay. Burnout could be end of the burnout, most probably. Of the burnout doesn't make sense because at the maybe so the region you cannot say whether it is end, start or end of the burnout. It starts when the radius is maximum. It keeps reducing and reaches the ambient pressure, right? So
Okay.
here, what has been asked with C star efficiency, uh, in practice, C star efficiency at burnout comes to be different than the initial value. Burnout will be more, less, equal to value at the ignition. That is what been asked. So it is not the end of the burnout. It's just at burnout. What is the C star? So maybe you can see it like the when the is the propellant and you reach the maximum radius. Okay, at that time C star, and you should compare that C star with the ignition C star.
Ignition C star is different from the equilibrium C star that is reached just after ignition.
Yeah, true.
Okay.
But throughout the equilibrium rise, whatever I observe, because I also work in solid propulsion system.
Okay.
Uh, but basically, whatever happens after the equilibrium is actually the C star almost remains constant. But before it attains equilibrium, the C star efficiency is going to be poor.
Why is it so? Like
Because
before
it
it.
at ignition you are not efficiently uh, doing the combustion, right? It's a ignition is at lower pressures. The pressure
Okay.
hasn't built up yet. So
Okay.
the pressure if the pressure is not high, your C star efficiency is low, right?
Okay. Got it.
So is that what the answer is? And yeah, C star efficiency
It's said to be
at burn,
more.
C star efficiency at the ignition. Yeah.
Okay. Okay.
Once
Thank
it
you.
passes ignition, it's
Yeah.
going to be almost constant always.
Okay.
There can be slight rise, but it's almost constant. All right. Any more questions?
Thank you so much, sir. Very helpful. And so this will be posted in the drive, right? Google Drive today, sir. Oh,
All right.
okay. Okay. Thank you so much.
All right.
Thank you. Bye. Good night.
Bye. Bye. Sham, I think. Okay, Sham also.